Sorry, keep going.
Done also the logic. But then at some point, Tasky in 1941 kind of revived the calculus of relations, emphasizing its algebraic nature, with the fact that it doesn't introduce any variables and multipliers, and he pursued an axiomatic approach, emphasizing the fact that you can have these tidy and clean axioms, stating, for example, that composition distributes over disjunction in the very same, let's say, I don't know, multiplication distributes over addition. Yeah, you emphasize this algebraic approach. Unfortunately, this relational approach decayed again when Monk in 1964 showed that the calculus of relations cannot be axiomatized by an equational solidization. Anyway, in computer science, the relational approach has some pretty nice applications. Maybe the most famous one is on relational databases, but also in this graph frameworks makes it very amenable to persistence, where you can get purely equational proofs. Recently, I found application also in rewriting, and one important mention also goes to problem logic, where, for example, OR and D in 1986 showed that the weakest precondition is residual on relations. Or also, Peter Owen in its incorrectness logic paper has relations. And I want to kind of emphasize this program logic point, because as we all know, also the logic is a major specification language. So the fact that the calculus of relation is strictly less expressive to it is kind of a shame, because we would like to reuse, for example, the results by OR and D on program specifications. So in this talk, we developed an algebra of relations using category theory. This is as expressive as full first order logic. It has a complete equational maximization, and the axioms arise from well-known algebraic structures. So basically, it brings to the first order logic realm all the desirable features of relation. Our starting point is Cartesian by categories by Carboni and Walters. This can be given a nice string diagrammatic presentation where we have generators and equations. Among the generators, we have this copier, which is basically a wire that's split in two. Also a discard, which is basically corresponds to close a wire. We also have the mirrored versions, co-copier and co-discard. Relations are represented as a box with a name on it. And then, as per usual, we have empty diagram, identity, symmetry, and we can compose all these things in sequence and in parallel, so we are in a symmetrical account. There are some axioms to be required. Now, if you think of, for example, this co-copier as kind of a multiplication, and this co-discard as a kind of a unit, then you will see that the axioms here in this row are the axioms of commutative monoids, and the one above, just mirrored, are co-commutative monoids. So pretty well-known algebraic structures. If you also add these two, you get special Frobenius algebras, and then there are also some adjoinance conditions, in particular, just saying that the monoid structure is left adjoint to the comonoid one, and the comonoid structures is lax natural, so these two inequality solved. The main example of Cartesian by category is the category sets relations. Objects are sets, arrows are relations. they can be composed sequence, and the composition in this category is the what is usually called relational product, where we have this formula with an existential quantifier and conjunction in the middle. Identity for this composition is the identity relation. We also have this copiers, which is the diagonal relation on a set, and the discard, which is basically a function that sends every element of a set to an element of a single dot set that I call star. Everything that comes in this gets discarded. Everything that comes in this gets called, if you want an operational meaning. You can imagine that the cocopier and codiscard are like the opposite relations of these. There are also, of course, the other products, symmetries, and so on, but I don't think the details are too important for this talk. So Cartesian bicategories are interesting because they correspond to a fragment, a regular logic, which is a fragment of associative logic, where you only have existential quantifier and conjunction as available connectors. And these are up translation. So, for example, take a predicate P. For simplicity, we only have one free variable, but can be easily generalized. This corresponds in the diagrammatic language to a box which has one wire on the left, which corresponds to the free variable. Conjunction is given by tensoring P and Q, and kind of unifying the free variables with the copier on the left. And another interesting one is the translation of the essentially quantified formula. So you have P here, it has one free wire on the left, which you close with this black dot, the unit. So you can think of this black dot as playing the role of the quantifier. It has been shown that the axioms of Cartesian bicategories are complete for regular logic, and we will see later what this means, let's say, formally. So one interesting thing that one can do is to think of co-Cartesian bicategory, which are kind of its dual. So to differentiate the syntagmatic presentation of Cartesian bicategories from the one of co-Cartesian, we simply swap all the colors. The background is black and the wires are white. But the generators are the same. You have copiers, co-copiers, discards, co-discards. You can compose in sequence and in parallel. And the axioms are pretty similar. You have again a special Frobenius algebra, but the adjointness condition and the naturality ones are reversed. So in this case, what is it? Monoid is left adjoint to the comonoid, and the comonoid structure is collapse now instead of Lux now. Okay, so the example of co-Cartesian bicategory is what I call the order category of relations. These are the same objects and arrows of the usual category of relations, but composition is different because you make kind of the Morgan dual of the original one. So here before there was an existential quantifier, and now it's replaced by a universal one. And here there is a disjunction that before was a conjunction. Identities are different, and these are the negation of the usual identities. The copier and discard are the negation, the complement of the original ones. So by duality, the internal language of this Cartesian bicategory is co-regular logic. The translation is pretty much the same, but the colors are swapped. And again, by duality, we can state that this completeness theorem. So the picture so far is that we have two categories of relations with the same objects, same arrows, different compositions and different identities. And moreover, we know that one is a Cartesian bicategory which models a certain fragment of FOL, and the other one is a co-Cartesian bicategory, which models another fragment of FOL. And what we want to do is to compose them together, make them interact to account for full first-order logic. So I spent some time on trying to understand how to compose two categories with the same objects and arrows with different composition, and I found out that there's knew it a lot of time ago. He knew that there were two compositional relations, and moreover, one linearly distributes over the other. That is, these two inclusions hold. 100 years later, Cocket and Kozlowski and Seeley categorified it in the definition of a linear bicategory. This consists of two bicategory structures sharing the same objects and arrows for different compositions, such that one linearly distributes over the other. That in the diagrammatic language, we represent it as these two inclusions of diagrams. You see, now we have mixed backgrounds, both white and black, because we want them together, like in these expressions here. So, for example, the fact that S is composed with Q in this operation is represented by this black background around S and Q. The fact that there is an external composition which is different from this one is given by external background, which is white. And you can do the same reasoning on all the others to see that they actually correspond to these diagrams. Now, starting from a linear bicategory, we define first-order bicategories. These are linear bicategories that additionally account for the Cartesian and co-Cartesian structures. So, yeah, so the bicategory is a linear bicategory, which additionally has one bicategory structure that is a Cartesian bicategory. The other one is a co-Cartesian bicategory, and all of these algebraic structures that you have in here are required to interact via linear adjunctions and linear version of the Frobenius axioms. Now, this may seem a little bit strange, but if you recall, in a Cartesian bicategory, you also have the structures of comonoids and monoids. They interact precisely via normal adjunctions and the normal version of the Frobenius axiom. In this case, they are all mixed. So we get these linear adjunctions, which, by the way, we didn't define it, it's in the Cocket paper. And also these linear versions of the Frobenius axiom. If you want a little bit more of intuitions, these two, so our logic is classical, and these two, this kind of linear adjunctions are what they, what give us excluded in the middle and no contradiction. Yeah. So, all in all, we can summarize the axioms of first-order bicategories in this picture. We have four algebraic structures at play: white comonoids, white monoids, black monoids, black comonoids. Separately, they're required to satisfy the axioms of special Frobenius algebras. They form special Frobenius algebras separately. Moreover, one is left adjoint to the other, and the other is right adjoint to the, I mean, there are adjointness conditions between the two. The bridge between these two worlds is precisely these linear Frobenius equations and the linear adjunctions. Some interesting properties that come in handy in proofs is that every onset of a first-order bicategory carries a Boolean algebra. You can define the usual constants and operations, so top and mid, bottom, and join. You may see already some kind of model equality, so either the negation of the other, also here. Negation diagrammatically basically swaps color. So if you have a diagram, you take a picture, you do the photographic negative, and you have this sketch. Or An example is, for example, the courier, which negative gets to the black courier and vice versa. So I'll show you an example of proofs. So let's take a non-trivial statement of the logic. This is valid implication. We translate it as an inclusion between diagrams. You can see here we have this alternation of quantifiers, both on the left-hand side and right-hand side. And in the diagrammatic form, this is reflected by the fact that we have these black and white dots, either inside or outside, I mean, depending on the alternation there on the polygon. Proofs are equational proofs. So we start from the left-hand side. Here we apply the laws of symmetric categories, basically deltas that we can put a black background around this diagram here. It doesn't change its meaning. We can use the adjournment condition to make appear this what is usually called a bone here on the left. What I call maps is a property of a certain set of arrows of so by categories, which is called maps, of which so this white dot is a map. And this property basically tells us that I take this white dot and push it inside the white border, and then it becomes black. I can do the same. So take this black dot, I push it inside the black border, and it becomes white. It's like it's I don't know, passing into a portal and change colors. So we use again one of the adjournment condition. We have these two white dots, one in front of the other. We can tie them up to an identity. Again, we will use the laws of symmetrical categories to remove this like borders around, which is not being telling anything special. So we get that in the last form. So we can talk about first of the theories, first of the diagrammatic theories. These are pairs made of a monoidal signature and a set of axioms. Now, to give you an example, let's take the theory of linear orders. Here the signature is given by a symbol R, which has arity1 and quality1. This is reflected in the diagrammatic language that we have this box with an R and only one wire on the left and one wire on the right. I, the set of axioms, is given by these four inequalities, which are basically saying that R is reflexive, transitive, symmetric, and total. Now, from a theory, we can build the free first order by category generated from a theory. And this allows us to get in a contour semantic approach a lot of years that tells us that models of a theory are in one-to-one correspondence with functors of the shape. That goes from the fitting, which is basically diagrams portioned by the axioms of the theory, to their semantic interpretation in red. And so we can state formally completeness, which says that for a theory, T, whenever so take two string diagrams, C and D, whenever their image along a functor, the shape F, is equal for every F, then you can derive this equality with the axioms of first order by category theory T. So they're equal semantically, then prove the equality in time. So string diagrams allows us to distinguish between what we call trivial and contradictory theories. A theory is trivial if this is provable in theory, and contradictory the same. This is provable. A trivial theory implies that all models of this theory have an empty domain. A contradictory theory has no models. This is interesting because theories correspond to propositional theories, and in this case, the axioms collapse to a deep inference system for propositional logic. This distinction allows us to generalize the completeness theorem, which only accounts for non-contradictory and non-trivial theories, while our proof, also supported by the frontera semantic approach, also account for the propositional case. And this is because, I mean, only in string diagrams you can do this kind of distinctions. These are both stating that true implies false, but this is doing in a wired way. Instead, here you have no wires. Okay, to conclude, we built a categorical algebra relation which is as expressive as first-order logic. The axiomatization is complete. The axioms arise from an interaction of well-known algebraic structures. It has all the desirable properties of a calculus of relations, like no variables, no quantifiers. If you see the papers, you will see that it encodes many other variable-free approaches, like versus existential graphs or quine predicate counter logic. And with the help of Davide Trotta, we also showed recently that there is an adjunction between the gallery of first order by category and Boolean doctrines, which is the other way of doing logic in category theory. When you put some restrictions on the Boolean doctrines, these becomes an equivalence. Which is also kind of, let's say, a sanity check of the definition of first order by categories, given that these are pretty well established. As a future work, we would like to go beyond the classical case, maybe account for intuitionistic or higher order logics. There is a known combinatorial characterization of string diagrams for Cartesian bicategories in terms of hypergraphs, open hypergraphs, and these kinds of give us, let's say, data structure for string diagrams, but also paves the way for a possible diagrammatic and hopefully interactive proof assistant for these kind of things. And also, I mean, we focus on the semantics of the logic rather than on the proof theory. So for moving to the proof theory, maybe an important, a possible path is to investigate better the connection with the inference that we found for the production case, and maybe generalize to the first of the one. So this is it. Thank you for your attention.
Yes. Grab the microphone.
Yeah, thanks. So formally, how do you interpret the background in the semantics, the color swap?
Oh, the color swap?
No, I mean when something slides through the boundary of the color, like is it like a functor box or something like that?
No, it's not a functor box. I mean, you mean this operation? Because
yeah,
it's like something. Well, the point is that, for example, take this diagram here. Here you are composing this generator here. So the external box is white, so in the white composition with this other diagram here. When you move it from here to the black one, change its color, you're simply saying that this white generator is composed in the black with the rest.
It is like continuous navigation.
It looks like something like that is going on. Maybe we can talk
Actually, now
afterwards.
that you made me think about it. Yeah.
Maybe next.
Any other questions? Okay, so I don't think we're going to have time for all of those. So let's pick one. Okay, think you're it.
Yeah, thank you for the talk. I was really impressed by the topic. So it's cool. So I'm wondering about doing the first order logic. So the whole first order logic, also with allowing multi-sorts. This is all okay. So about you have a completeness and soundness with respect to this setting of relations. Do you have soundness with respect to other settings too, or does it like go to any other partition by category as well, or is this specifically working in the setting of relations?
No, actually, here in the Montoya semantic thing, this can be any sort of category, not necessarily that, but I kind of like the fact that I got this semantic syntax and this semantics. So I think putting that there was just so it has soundness in other settings, and in any partition by. So yeah, okay.
Okay, thanks very much. Let's speak. Is it this one up next? Yep. Okay. That's the right. Control L. Thanks. I do not normally use Windows. Okay. Yeah. Oh yes, yeah. Oh. Okay, cool. So for our next talk, we've got Pablo Donato talking about the flower calculus.
Thanks. So thanks to the organizers for accepting my invitation. So I'm going to talk about the flower calculus, which is a recent work that I've been doing in the context of my PhD thesis. Okay, I don't know how to use this.
You might need to click once on the slides.
Okay. Yeah, so can I point with the... How does it work? Okay. No.
So up or down to go forwards, and that's the red one should be the laser pointer.
Okay, perfect. Thank you. Okay, so the overall aim of my thesis was to design new kinds of graphical user interfaces for interactive theorem provers or proof assistants. And so the methodology that I employed was basically to do graphical calculi, like the one we've seen in the previous talk. And so the diagrams will represent statements, logical statements, and then I designed inference rules on the diagrams for systems. And the idea is that the rules correspond to direct manipulation actions in the graphical user interface. Okay, so the main inspiration behind this work is a formalism invented by Peirce at the end of the 19th century called existential graphs for classical logic. And this is basically an informal version of the system you've just seen in the previous talk. And so in 2010, Ustra introduced an intuitionistic variant of existential graphs. And basically, the flower calculus is yet another intuitionistic variant, but which I have designed with proof theoretical questions in mind, and in particular, it satisfies an analyticity theorem, kind of like the subformula property in sequence calculus. And this is called the flower calculus because I like to represent the statements as flowers. It's a nice metaphor. Okay, so there is no category theory involved at all in this talk, but I would be pleased if you see any way of formalizing any of this in category theory and have some discussions afterwards. So I'm first going to introduce quickly the existential graph pairs of pairs. Then I'm going to introduce my flowers and how they come historically from, I can tweak a bit the representation to get into flowers. Then I'm going to show how to reason with flowers, inference rules, and do a bit of meta theory, in particular soundness, completeness, and how to get kind of cut elimination. And finally, if I have time, I'm going to show you an implementation of the flower calculus that I call the flower prover. So it's just a graphical interface that turns in our web browser. Okay. So existential graphs. So as I said, it's a diagrammatic proof system invented by Peirce. And basically, there are three different systems called alpha, beta, and gamma. And the first one, alpha, is for propositional logic. Second one, first order logic. And the last one, a bit more experimental. It has been interpreted as being for higher order nodal logic, but at the time, tautologics didn't exist at all. Even first order logic was very new. So we're just going to focus here on alpha. And there are three basic kinds of diagrams in alpha, which Peirce called icons. The first one, the most fundamental one, is called the sheet of assertion. And it's based on one convention that if you write something on the sheet of assertion, which in this case will just be the space of the slides, okay, I can just scribe things on the slide. And if I write A, it means that I assert that A is true. Very simple. And in particular, if I write nothing on the sheet, if it is empty, it means that I assert nothing. So it's trivially true. Then I can put things next to each other, juxtapose them, and it's just interpreted as conjunction. Both G and H are true, which is very natural. And then I have this so-called cut, which is basically enclosing some area in some closed curve. And here, like in the previous talk, I'm picturing it by shading the contents, like the interior of the curve in negative. And so this is negation. I assert that G is not true. And so with just negation and conjunction, it's well known that in classical logic, I can just encode all the other propositional connectives. So false code is just black dot, which circles the empty space. So not true is false. Not A and not B is A or B, and I can do the same with negation. So next, I need some inference rules to have a proof system. So here, I like to think of them as addition principles, like when you edit some text on your computer. And so Peirce called these rules relative transformations. The first transformation is called iteration. And this is just a principle of, like, you can copy paste some parts of the sheet of assertion. So here, if I have some graph G, which is next to some other graph H, I can just copy G inside of H. Okay, it's a bit informal, but we will see some examples. And conversely, I can, with the iteration, I can just unpaste my graph. So these two rules work in context of any polarity. That is, it doesn't matter what color the background is. Then I have insertion, which states that I can just insert any graph in a negative area, and deletion, the dual, that I can erase any graph in a positive area. And the last principle is more of a topological or space principle. And it says that if I have a double cut, two cuts nested inside each other, which forms this kind of ring, I can erase the ring or insert it around the graph G. And I like to think of this as a kind of topological deformation, just collapse the two cuts on themselves. So an example of proof in the system, here I'm going to simulate modus ponens. So I just start with this assertion that both A and A implies B are true. This is one way of interpreting this graph. And so first rule that I can apply is the iteration. So I can justify the white A by the black A and erase it. And then I can erase the double cut. So think of it as double negation elimination. And then I can just erase A to obtain B, because A is in a positive area. Okay, so that was existential graphs. Now I'm going to show you how to get flowers out of them. And I'm going to start from another idea from Peirce, which is called the scroll. So Peirce has this idea that the most basic form of reasoning is hypothetical reasoning, which is a common idea in proof theory. And so he would represent this with this so-called scroll, which is, again, a self-closing curve. But the important thing is that it is self-closing. It is like there is this little loop which intersects exactly in one point. And so this is interpreted as implication, but classical implication. So A and B implies C and D. And so the outer loop, the outer area is the antecedent, and the inner area is a consequence of implication. And in classical logic, this is really equivalent to having this negation encoding of implication. So you can see it as two nested cuts. But I emphasize this continuity of the line with this self-intersection point. And another interesting historical fact is that it was Peirce who introduced the very symbol of implication into symbolic logic. He thought that it was an important concept that deserved a separate symbol. So then we go to fast forward to 2010, and Ustra introduced the generalization of the scroll called the n-ary scroll, which is basically a scroll, but with any number of inside loops or nested cuts inside. So here, this is an n-ary scroll with 5 loops. And if I want to interpret this logically, I can just combine my previous interpretations. So here, if I have 2 nested cuts like this, B and C, I interpreted it as disjunction, here as implication like this. So I just combine the 2, and it gives me that the outer loop implies the disjunction of all the inner loops. Yeah, and there is some dots, which is important because, yeah, this is again the thing about continuity. This is where intuitionistic logic comes in, because the representation allows me to distinguish between the negation encoding, classical encoding of implication on the left, and the real true intuitionistic disjunction, which is this continuous version. And the same applies to implication. So yeah. And this is the case where n equals 1 for the first scroll, and the case where n equals 0 is just the cut. And it also works like, since if you take the disjunction of an empty set of in loops, it's just falsehood, and you get the intuitionistic reading of negation. A implies false. And so finally, flowers come into the picture. Basically, I didn't really like this representation. It reminded me of like the cylinder of a pistol. Okay. And so I just had this idea of, again, doing a continuous deformation by turning the in loops inside out, and this gave the flowers. And so now I'm happy. Another trivia. Peirce, in one of his manuscripts, described the origin of the terms theorem and corollary. And actually, a corollary was depicted like people would put a little garland or flower corolla besides the name of the corollary. And if you think about it, it's a fun coincidence because the corolla, the petals, so the corolla of the flower in my representation, they're literally corollaries of the pistil, you know, they're directly implied by the pistil. Okay. And last thing, so I'm going to go very quickly, but I can also add a quantification to the picture. So I'm not going to use lines like in the previous talk. I'm just going to use binders, which are more practical when you have a lot of different variables. And so basically the idea is that if you have a binder, which is represented by this pink X here, if the binder lies in a petal, you interpret it as existential quantification. And if it lies in the pistil, it's just universal quantification. And then, so I call a garden the content of an area which contains both binders like this and flowers. So now I'm going to show you how to reason with flowers. And so basically it will be the same rules that you have in existential graphs, but a bit modified. So here the iteration and the iteration principle or copy-paste principles. Basically I have two variants. In one case, I can copy something which lies outside of the flower, inside of a flower. This is cross-pollination. And then you can copy something inside of a pistil into any of the petals. And I call this self-pollination. So an example here, so this works at an arbitrary depth. So for example, if I want to justify this A here, by this one, I can just unpaste it like this. Okay. And this works because you can imagine the A traveling here. I don't know, maybe pushing the metaphor too far, but yeah, okay, it's like wind pollination. And then you have self-pollination, so basically I can duplicate this B and put it here. Okay. So the insertion and deletion principles also apply here, but I have to have to split them in two versions, one for flowers, so I can grow a flower in a positive area or proper for a flower in a negative area. And for petals, I can kind of like glue them, add in a negative area a petal, and I can also pull a petal in a positive area. And importantly here, I write the rules in this direction from conclusion to premise. So logically, this means that the right-hand side implies the left-hand side. Okay. So there is another rule, which is basically a restricted version of the double cut principle, where I could erase, some double negation. But here it has to be intuitionistic. So it looks like this. I can enclose some graph or some flower in a petal with an empty pistil attached to it. I call this crawling in terms to versus crawl. Then you need some rules to handle reasoning with quantifiers. And so here it's just, you can instantiate the quantifier. So if you have a universal quantifier by having the binder in a pistil, then you can instantiate it and with some arbitrary first order term. And it will instantiate it both in the pistil and all the petals. And for existential quantification, where the binder lies in a petal, well, it will just instantiate the term in the petal, but it will also duplicate. So in both rules, I duplicate either the petal or the flower. And this has interesting proof theoretical property that I will come to quickly. Okay, so this is just the dual of instantiation. I can start from a concrete statement on some term T, and I can generalize it by introducing a binder, either universal or existential. Okay. So this is the most complicated rule, I guess. Here you have to interpret the color as, okay, I can fill area of the petal or the pistil with any content. And basically this is a form of case reasoning. You assume a disjunction, the red petals here, of statements. And to prove this, you just need to prove all of the different cases. So this is a conjunction here of the different cases. And you will duplicate this outer corolla. Okay. It might seem a bit mysterious, but it's just case reasoning. And a special case where there are no petals at all, it collapses to the X-falso Quasi-Bed principle. So this pistil with no petals represents absurdity or falsehood. And if you assume an absurdity, then you just get this petal with this flower as an empty petal, which is trivially true. And last rule, if you have a flower with an empty petal, which is what I just explained, then it is trivially true, you can erase it. So I don't have time, I think, for an example proof in the flower calculus, but I'm going to go straight into meta theory. So there is this distinction. You can make this distinction in the rules between what I call natural rules and cultural rules. So what is it? Basically, so the natural rules are the union of all these groups of rules. So the iteration, instantiations, calling, case reasoning, etc. And an interesting property of these rules is that they are all invertible. This means that if I rewrite some bouquet of flowers, it's a multi-set of flowers. So if I rewrite a bunch of flowers into another bunch of flowers with one of these rules, then the two bouquets are equivalent, logically. So this allows some form of equational reasoning. And then another very interesting property is that these rules are analytic in the sense that if I rewrite phi into psi, and if A, so take some atomic proposition A occurring in psi, then I'm guaranteed that it also occurs in the bouquet phi. So this reduces the proof surface because I know that if I want to apply some natural rule, I don't have to come up with some arbitrary flower, which doesn't appear in my initial goal, which is phi here. And then I have the cultural rules, which are all the other rules. So insertion, deletion, abstraction. And so they have, so they do not satisfy all the properties of the natural. So all of them are non-invertible. So you might, when going from phi to psi, you might break the probability of your, okay, 5 minutes. You might break the probability of your goal. And yeah, some of them are also non-analytic, like the cut rule in sequence calculus. So yeah, basically, maybe I haven't been very clear about this, but in this paradigm, the act of proving some flower is just amounts to erasing it. So you start from the goal you want to prove, and then you erase it, and since the empty space represents truth, then you have proved it. So this is a kind of backward proof. And you can do this in any context. The rewriting works at any depth inside your diagrams. And so, yeah, this is a bit technical, but you can define the notion of hypothetical probability. So you can say that some bouquet psi is provable from some bouquet phi, which I write like this, traditional notation. If in any context X, so by context, I mean some bouquet where there is just a specified location, which I call a hole, and where in the hole I can plug any other bouquet. And so if I plug, if I plug some bouquet here in my context, and if I can erase it in that context, and if in the context I have the hypothesis phi, then with some notion of what is a hypothesis, which is related to the notion of pollination that I introduced earlier, then I can just erase psi. That is prove psi given that I know phi. And with this notion of hypothetical probability, I can prove the standard meta theorems. So I have soundness. If I have some rewriting, this means that the right-hand side implies the left-hand side. And I do this by giving a Kripke semantics to the flowers. So intuitionistic semantics. And completeness in the other direction, if some bouquet entails semantically another bouquet, then it means that I can prove it. But importantly here, I can prove it only with natural rules. I don't need all the cultural rules. So this means that all the cultural rules are admissible, and this is the equivalent of a kind of cut elimination theorem. And this entails in particular that I can work only in the natural fragment, which is analytic, and also invertible, which is useful for doing proofs and searching for proofs. Okay, I have 1 minute left, I think. Very, very quick demonstration. Okay, I think I can. Okay. So basically, I have two modes in this interface where I can click on flowers with natural rules and with edit mode where I can insert or delete flowers, which correspond to the cultural rules. And yeah, I can do a bunch of things like convert them into equivalent formulas. Yeah, so yeah, it's a bit hard to explain, but basically the boxes represent flowers, and the upper part is the pistil, and the lower part the petals. So here, for example, I have a disjunction. I can do case reasoning. Okay, and I can pollinate some flower, bring it like this. Then I can justify this B. Okay, so I'm going very quickly, but okay. And then I also have some form of automation. I can click here, and here it will be able to automatically apply my hypothesis here. So I can just. Okay, so that's it for me. A bunch of related works. I'm just going maybe to emphasize some interesting connections that might relate to this community. In particular, I've noticed this connection. So if you want to interpret an arbitrary flower as a formula, here you get what is called topo theory and categorical logic. This is just a coherent formula or geometric if you have an infinite number of petals. So yeah, I haven't investigated this connection, but interesting. Thanks for your attention.
Time for some quick questions.
So you said the purpose was for proof theory. So do you get cut-free proofs sort of automatically out of this?
I mean, it's hard to talk about cut-free proof because I don't have notion cut exactly. I will need some translation to sequence calculus, which is possible, by the way. I've done it in formalized in Coq. But yeah, basically it's just what I mentioned about the analyticity results. The fact that I can just do all my proofs in the natural fragment of the calculus means that I have some form of cut-free proofs, which is complete for probability. And then I don't have, so this result is a kind of semantic cut elimination. I don't have a procedure to eliminate the equivalent of cuts into the proofs, but I still get the admissibility of all the rules which are non-analytic. So yeah.
Any further questions?
Right. So you have mentioned that the property of analyticity helps in automation, at least for the proof
Yes.
search. But do you have more evidence that indeed it does help? For example, efficiency, your proof search as compared with alternative procedures?
I haven't directly compared with alternative procedures. Again, it's a bit hard because formalism is very different. from what we're used to, but basically the only evidence I have now is this little button here, which automates most of the rules. And then you can think of it as the only rules that you really need to apply manually are like, okay, there's there is this drag and drop rule where you need to import some statement into a different context, different location. And also, yeah, case reasoning can quickly become very complex if you have many cases. So you might want to apply case reasoning manually too. But apart from these two forms of reasoning, you can automate everything. So I don't know in practice, in real context, doing real math, if it helps that much. I don't know how it compares to existing automation, but yeah, that's where I'm at currently.
That's your question, quick, Jamie.
Yeah, do you feel you get additional or different insight when you represent proofs using this notation?
So the current problem with this representation is that the proof is very dynamic. It's just a sequence of transformations on the diagram. But I have this idea where you could record the information of the proof along the transformations. Well, for example, if I if I just justify, I don't know, okay, if I just justify this B with this one, I could just have a kind of type theoretical encoding where here it is the argument of a function, and when I click, it just keeps track of the application of the function to the argument. So you could just keep the boxes and put a lot of term annotations inside them and get a proof representation. Yeah, it's very informal for now, but I've noticed maybe some connections with neutral forms and normal forms in lambda calculus. So, yeah.
Thanks very much. Let's have a
Realize that the screen share is only for the slides. If we're doing a demo, you should share the whole thing.
Okay.
Did you read? Oh, okay. You might just share again.
Control L.
And then Zoom screen share.
Is it not still showing?
Are we? Did you want me to?
Yeah, that's fine. Yeah, it's not reserving.
Okay. New share? Oh, what it is? Oh,
Yeah,
no.
just click on the new share.
Okay. And whole screen.
Screen is top corner.
Cool. Great. Hopefully that's working. Cool. Oh.
Yes.
Okay.
The hide floating meter controls.
Cool.
Cool. Okay, so for the
You need to click on that for a second. Yeah. Cool.
okay.
Yes. Thank you.
And so for the third talk of the session, we'll have Niku talking about homotopy.io.
Thank you. Thank you for the invitation. Callan's going to give half the presentation too. But this is joint work with quite a few collaborators. Jamie's there in the audience. I think Nathan is online. Yeah, we're around in general. So our tool, homotopy.io, a lot of you might have seen it before in lots of different other contexts. But this talk is just going to be about the implementation and sort of, it's kind of an experience report of things that we, how we implemented it and things that we found. So I know we're at the last session before lunch, and the previous speaker promised no category theory in his talk. I think our talk might have no maths, so bear with us. I'm going to keep it light. Okay, so like I said, I'm going to split the presentation. So I'm just going to present a few slides, just some background about the tool, and then Callan will show a little demo. Okay, so what is homotopy.io? Well, homotopy.io looks a little bit something like this when you're in it. It's a graphical proof assistant. for working with finitely presented semi-strict higher categories in the form of n-dimensional string diagrams. We wrote it in Rust. It compiles to WebAssembly and it runs entirely in your web browser. So you don't need to install anything to use it. And you can just access it at that URL if you're ever curious. You can use it for simple things like just drawing some ticks for some string diagrams if you feel so inclined. But its real value is that it's like a proof assistant. And what that means is you can use it to build up a complex string diagrammatic argument step by step, and the system will check and make sure that each step you've done is admissible and it is meaningful. Interaction all happens through a point-and-click interface with the mouse, more or less. And those interactions will trigger recursive algorithms which manipulate the underlying combinatorial encodings of the string diagrams that are in our implementation. I'm not going to have loads of time to go through these different algorithms that we've implemented, but please see our accompanying paper and there's kind of a large body of work on homotopy.io already that talks about this stuff in detail, and in particular its categorical semantics and justification for why it's doing something sensible. So new features. We now have support for fully coherent inversible generators, which means that when you are inputting your algebraic signature, you can mark certain pieces of the signature as inversible. And that's really helpful for working with equational theories of string diagrams. So a previous version of the system, you'd have to, if you wanted to add an associativity law, you'd have to add both sides. And then maybe you had some higher coherence that that you'd want to use, but the system wouldn't know about it. But now you have that. Another thing that is reasonably new is you can share, you can save your proofs and you can share them with others by URL. And you can publish them permanently on the homotopy.io website. So that could be useful if you wanted to write a paper and you're using it as a tool and you want to include a reference to your interactive string diagrammatic proof. Okay, so string diagrams. I think lots of this crowd will have seen string diagrams before, but let me just briefly give an overview of how I view them. I think that string diagrams provide a good graphical calculus for reasoning about morphisms inside of monoidal categories. Now, in a certain vein, monoidal categories are like a special case of higher categories. So if you want to generalize away from the setting of monoidal categories to higher categories, then what you should get is some sort of generalized string diagram. And the thing that you get is a form of string diagram which is topologically n-dimensional. So homotopy.io is based on a particular model of higher category called associative n categories, which really has this idea at its core. The model is strictly associative and unital, which means that there's no ambiguity in how you might bracket this, and you don't care about how long these wires are. But it has weak interchange. And what weak interchange means is that every admissible deformation of an n-dimensional string diagram is, in some sense, proof relevant. So what that means is if you have an n-dimensional string diagram and you do some manipulation on it, what that does is it generates an n+1 dimensional cell, which begins with your source and ends at the target. You'll see what that looks like in a second. And then you can render that as n+1 dimensional topology in our tool. We have rendering all the way from 0 to 4 dimensions. Another way of sort of saying that is that instead of having equalities between different string diagrams, we have directed rewrites between them, which have data attached. Okay, so if you would consider this two-dimensional string diagram here, then an admissible deformation would be the interchange of the morphisms F and G. So if you imagine pulling this down and pulling that up, that is an isotopy of string diagrams, which is, you know, very standard in string diagrammatic reasoning. So if we were to perform that move, what we have is the diagram on the previous slide on the left, and the result of the move on the right. And you can think of this whole process itself as generating a three-dimensional string diagram, where the central slice is the singular moment where F and G occupy the same height. So our tool is capable of rendering that move as three-dimensional geometry, which is a braid. If you look closely, if you trace the path of this F, that corresponds to this yellow wire, and the trace path of the G behind it corresponds to the red wire. And using our tool, the user will be able to pan around the geometry almost like a video game. And also we can render four-dimensional geometry as an interactive animation of three-dimensional geometry evolving over time. You'll see that in the demo. I think this is a good opportunity to say that we have real-world applications. So if you'd like to pass these around, we've 3D printed some of these 3D geometry. Oh, no.
We'll see some in a.
Yeah, unfortunately, I can't touch
we
those.
can't really print them.
Yeah. Although we could print them as slices. So the primary interface of the tool is really the display and manipulation of these 2D slices. And I talked about this multiple move, and the way that you would get that is you are presented with something like this, and you really just click and drag this F node down once. That would give you this central slice, and then you could click and drag the F node again, and that would give you this final slice. So every time you give input to the tool, it will either tell you that the move that you've done is inadmissible, which is very possible if you imagine working in sort of some two-dimensional slice of some seven-dimensional geometry. You can't see all of the various obstructions. Or it is admissible and it will generate a rewrite of diagram. So that's sort of this piece going forward from this slice to this slice. And then apply that to show the new state. So in this case, the move is admissible, so the tool responds, well, it lets you build this. Okay, so I have here some pseudocode for the data structures which underlie diagrams and rewrites on the tool. They are defined recursively, and we use sort of a lightweight dependent typing to distinguish between zero-dimensional things and higher dimensional things. So diagrams, bottom, they are either zero-dimensional, in which case they consist of something we call a generator, which is essentially a name, or they are higher dimensional, in which case they consist of a source diagram and a list of cospans which will iteratively rewrite that source diagram backwards and forwards from the source to the target. It will become a bit clearer what that means in a minute. A rewrite between diagrams is also going to be either a zero-dimensional thing or a higher dimensional thing. And if it's zero-dimensional, it's either the identity rewrite or it just maps sort of the underlying zero diagrams from source to target. And it's also equipped with something we call a framing. And the framing is like the direction of a rewrite with respect to its coordinate system in n-dimensional space. So in 2 dimensions, that might be saying something like this rewrite has the directionality north to south. That's used internally in generating the coherently invertible structure, and also plays a role in sort of type checking our diagrams to make sure that they're valid string diagrams. A rewrite between higher dimensional things is given by a list of cones. And what these cones do is they sparsely encode a collection of rewrites between n-dimensional diagrams inside of this field called slices. The intuition for what's going on there is that in an n-dimensional string diagram, if you imagine this n-dimensional space and you take any given point, the surrounding local piece of diagram is likely to sort of be the identity everywhere. And you kind of want to elide these things because there's going to be loads of them and nothing interesting is happening in most of the diagram. So it's analogous to how if you wanted to represent a directed graph on a computer, you can choose between an adjacency list or an adjacency matrix, and you might call the adjacency list representation a sparse encoding of the edge relation because it doesn't need to store mostly non-instances of edges. So here's a bit of a worked example. The picture on the left is a two-dimensional string diagram. And if you were to scan horizontally up the page, horizontal slices, you see that each slice itself can be thought of as a one-dimensional string diagram. The very first slice, which we call R0, intersects with the wire 3 times, which is why we write this 3 here. It's also indistinguishable from the slice which is ever so slightly above it. It's also indistinguishable from this slice, and so on until you get to this slice where something starts happening in the diagram. And we call that the first singular slice, or S0, and that you'll see that that intersects with the wire and these two morphism-shaped things. The same is sort of true for sort of this region between S0 and S1, that you could pick any of these slices and they all sort of do the same thing. And we use this to stratify the diagram into what we call regular and singular levels. Now, using our encoding, this two-dimensional diagram is then given by just this source slice, plus the collection of rewrites, which will rewrite it forwards and backwards until the target slice here. So that's what I mean by an n-dimensional diagram. In this case, n is equal to 2, is given by a source slice and a list of postmodes. So here is another picture which shows the sort of full structure, and it makes all of the underlying zero-dimensional diagrams and zero-dimensional rewrites clear. It's not in the picture, but typically one would want to work with diagrams that are with respect to some sort of algebraic signature. So by that I mean one in which each of these points has some kind of type information attached to them. So for instance, this piece of diagram here, well, it's got two things that if you were to draw it as a string diagram of 2 legs coming in, and it's sort of got like 1 leg coming out. So if we called this dot here an M, and we said that these wires are called A, then what that thing might naturally represent is the string diagram for a monoid with carrier A. We also don't have the framing data drawn on here, but one thing that it would let us do, for instance, is distinguish between the left leg coming into the monoid and the right leg coming into the monoid. I do have the time. Okay. Yeah, okay. So I just wanted to give a bit of a flavor of the kind of algorithmic tools we have. So this is a picture of what we call our contraction algorithm, which is what you get when you try to squash diagrams. And you obtain this by clicking and dragging the bottom left bead upwards or the top right bead downwards. And this will shrink the diagram on the left, which has 2 singular levels, to the diagram on the right, which only has 1 singular level. And what this is sort of internally doing is computing some kind of co-limit of the iterated co-span on the left, which is this guy, and which would give you this singular level on the right, and then it reconstitutes the rest of the diagram from that. And because it's a co-limit, it means that it's like a canonical way to shrink the diagram, and it doesn't always exist because not every contraction move will be admissible. So there's more detail of the different algorithms we use in the paper, but I should swiftly move on to demo.
Cool. Thank you, Nick. So now I'm just going to give a quick demo showing what the tool looks like. So like Nick said, the tool runs in the web browser, and you can just access it at beta.homotopy.io, and we hope to soon be able to drop the beta from the URL when it's stable enough. So when you first open the tool, thanks, you're presented with an empty workspace, and basically the two main components of Homotopy are we have this workspace in the middle, and here on the left we have the signature. So Homotopy lets you work with freely generated end categories. So you need to give a list of generators, a final list of generators, which is the signature. And then in the workspace, you can construct any diagram which is valid in the end category generated by those generators. So when you first open the tool, you have no generators, it's an empty signature. So we can add the generator by pressing A, as the text here indicates on the keyboards. And that just adds a zero-dimensional generator. You see here, it says 0 because it's zero-dimensional. It has a name. You can open the settings panel to say change its color or rename it. So I might call it X for this sock. And now to add the one-dimensional generator, we need to specify a source and a target. So to do that, first I need to decide what the source is. So say that I want the source to be X. I just click on X to bring it into the workspace. And then I press S on the keyboard for source. And that will just sort of stash the generator into the corner and say there is the source. So you remember what the source is. And now I want X to also be the target. So I'll click on X again. It will bring me into the workspace. Now I press T for targets. And as soon as I do that, it will add the new generator, which is one-dimensional. So I'll call this F now. And maybe I'll make this blue, which goes from X to X. So this is like a one-cell F with source X and target X. And now we can keep going. So for example, if I want to do monoids, and maybe I can do the associated that people were passing out, the black one that Yanis has. So I might want to add the monoid multiplication. So I can click on F to bring it into the workspace. And now I can just click on the target of F to compose it with itself. So now I have F composed with F. So that would be the source of the multiplication of a monoid. So I'll click source. And now I want the target to be just one copy of F. So I'll click targets. And what I have now is a two-dimensional cell, which goes from F composed with F to F, and is rendered as a 2D string diagram. Now you would expect with a monoid that the multiplication is associative. So I will now add the associativity condition. So to do that, we need to start with the left-hand side of associativity is a multiplication of three things, brackets in the left. So I can do that by just clicking on this leg here at the bottom to compose it with another multiplication. So I have 3 wires, and I first multiply the first 2 wires and then multiply with the third wire. So this will be the left-hand side of associativity, so I'll save it as the source. And now the right-hand side should be the same thing, but just now bracketed on the right. So I'll just click on the other leg to add another multiplication and click targets. So this added, so if I call this mu for multiplication, I'll call this multiplication. I now have an associativity pre-cell. So when you click on it, it first renders in a 2D projection because 2D is usually it's the only one that's interactive. But you see here in the top right corner, we have 3 tiles called VVP. So we have 3 because this is a 3-dimensional cell. And what the V means, it means that we're viewing the first 2 dimensions and we're projecting the third dimension. So now if I want to view this as a 3D cell, I just need to click on this P to turn into a V. And now I can just view this as a 3D diagram, which is exactly the same one that we 3D printed, the one that Yanis has. So you can just interact with it in 3D and view from all angles. And you can also, we can also view diagrams in 4D. So I'm not gonna build it live, but I downloaded an example earlier. So this is a proof of some facts about the third homotopy group of the 2 sphere. And you can view this proof as a 3D object, or you can also view it as a 4D object, which is a movie of 3D objects. So we have here basically a YouTube play bar, so you can just play this as a video. It's not animation. So see, basically your proof just comes alive. And this was actually quite tricky to do because we want to make sure that these animations are smooth. It's very easy to just do a discrete animation where things just sort of jump around. We want to make sure that these are like smooth. And obviously our encoding of the diagrams is very discrete, so we have to do some work to make these into smooth animations. And I'll probably end it there because probably all hungry and want to go to lunch.
Thank you.
Thank you.
Thanks very much. Are there any questions? Wheels?
Yes.
A while back, I was doing something in an old-fashioned way. A while back, I was doing something with old-fashioned ways of drawing diagrams. They were rather similar to the ones in Schwan Longstalk yesterday. Jamie said to me, "Oh no, that's wrong. That's unnecessarily difficult. Here, you can do this with string diagrams, right?" And I say, "Yeah, they're great." So I wonder whether you do you have a way of turning your string diagrams back into old-fashioned, morphisms and arrows and naturality squares and so on, in the old-fashioned style? Well, maybe Jamie can answer that one.
Yeah, I mean, oh, okay. So, yes, you absolutely can turn them back into what you think of as like morphisms and naturality squares and stuff like that. But the problem is we're working, well, not problem, but we are working in a higher model, a model of higher category. So in particular, this associative n category thing. So if you are familiar with sort of like tri-categories versus, or strictification of a bi-category perhaps, a tri-category cannot be strictified fully, but there is a kind of gadget called a gray category, which strictifies it as much as possible, and associative n categories are like a moral extension of this into n dimensions. So the diagrams that we do have, they represent specific terms in this model of higher category, and it does agree with, if you restrict yourself to 2 dimensions, it does agree with the normal notions of string like terms in a strictified bi-category type of thing. Does that answer the question?
I was just wondering whether your tool does it.
Oh,
The tool doesn't do it now.
No, tool doesn't.
It could be interesting to try, but we will.
Yeah.
It will become very difficult in higher dimensions.
Yeah.
Of course, yeah.
Any other questions? I've got a question as well. So, have you at all looked at kind of applying this to the sort of things that people do in ZX calculus and these sort of string diagrams, kind of representing the rewrites of those in this multi-dimensional way?
The two of us haven't personally thought about it, but I feel like Jamie might have thought about it.
So my question was whether you've kind of used these tools to kind of represent rewrites of ZX diagrams in this kind of nice 3-dimensional way.
Yes, we get our master students to do that. They use that.
Cool, nice, thanks. There's a question at the back.
I could just speak loudly.
Yeah, I think that might not be picked up for the online participants.
Cool, thanks for the talk. Similar question to Paul's. Do you have a tool? Is there a way of exporting these diagrams if you wanted to include one in tech, for example?
You can export it
as a text diagram.
Yeah.
Okay. Oh,
yeah.
wonderful.
I didn't show it in the interface, but there's a panel somewhere where you can export to text.
Yeah.
So you get literally like this picture here. You literally get a copy of this in text, and you can just include it in your documents.
Or SVG.
Yeah.
Or
obviously, this only works for 2D. For 3D, we don't have an. I guess you could just take you could download like a PNG.
Well, for 3D, you can download the STL and print it.
Yeah, or you could 3D print it if you happen to have a 3D printer at home.
So, I just wonder how much automation of the proofs you have in your tool.
So it's yeah, we don't really have anything like tactics or anything like that. It's sort of hard to think about what it might mean to move towards sort of a goal. You need some sort of interface to input the kind of goal that you were looking for. And then there's quite a large space of possible moves, which grows exponentially with dimension. And I guess the thesis is that if you're a topologist or something and you're looking at it, you might know what to do. But I don't think, we haven't thought about how you might encode the right thing to do as a tactic.
Thank you.
Cool. I think we've got time for one quick question, if there's any more. Yep.
Yeah, thank you for the talk. Are there any plans of implementing these systems in other data improvers? Like you have Lean, and if somebody wants to prove something in Lean and they want to use, let's say, these kind of tools, would there be interaction between these systems?
There is a long-term plan to connect HomosPR to the type theory cats for semi-strict omega categories. And then in theory, you should be able to also link that to ACTA or like multi-log type theory. So in the long term, it might be possible that you have like some proof in ACTA, multi-log type theory, and you convert it into cats, and then you convert it to HomosPR. You manipulate it as a string diagram, and then you convert it all the way back.
Okay.
But it's a long-term goal, I think.
Okay, that's very cool. Yeah, thank you.
Okay, thanks very much. Let's thank the speakers again. Anybody going to step on after back at the computer science building where we were yesterday?
We just need to stop recording. So stop share, and I think it's not recording. Yes, and then I think